Okay, so today we're going to talk about the fundamental theorem of calculus. And see, I really like this whole um, topic. It's because what the fundamental theorem of calculus does is it just kind of takes all of calculus and tries to summarize it in this one theorem. That's why it's kind of like called the fundamental theorem. So a couple of comments I want to make before we get into it is the fundamental theorem of calculus is named the way it is because it makes connections between the two branches of calculus. And the two branches are differential and integral calculus. So we already know, see, differential calculus is what we talked about all of first semester. And now integral calculus is basically what we're talking about this semester. So the second comment I want to make, and then we'll get into the fundamental theorem of calculus, is that derivatives and integrals are closely related. And we know what the relationship between derivatives and integrals are, or we'll actually discover it here also. They are, in fact, inverse processes. Okay, so what you'll notice is derivatives and integrals, they're in fact inverse processes. And so once we talk about the fundamental theorem of calculus, then we'll kind of see how they are related. So before I give you the official fundamental theorem of calculus, we're going to break it up into two parts. So we will break the fundamental theorem of calculus into two parts. And then we'll combine them. So then combine as one. So the way our book approaches this, I kind of don't like it. It's part one. I would probably talk about second. Now, it doesn't really matter. Some books may call part one, part two, or vice versa. So I'm just gonna, just to stay consistent with the book, I'm gonna call part one whatever the book calls it, and then part two whatever the book calls it. But I'm gonna start with part two first, okay? Because I feel like through part two, part one becomes so much easier. Without talking about part two first, part one may be a little more complicated. So here's what we're going to do. Let's define FTC part two. Because for me, at least, if I know part two, part one becomes so much easier. So if f is continuous on the closed interval from a to b, then the integral from a to b of f of x dx. And notice how we're talking about the definite integral. So guess what? Fundamental theorem of calculus part two is now going to teach you the shortcut. So what we learned in section two, which was the long way where we used the definition of an integral to evaluate this, we're going to learn the shortcut now, which equals to capital F of b minus capital F of a. And see, capital F, we're going to say where capital F is any anti-inverse derivative of f. That is a function such that the derivative of capital F will take you back to lowercase f. So look at what this is saying. This is basically our shortcut, isn't it? Because what it's saying is, look, if you want to find the area under the curve of f of x from a to b, all you have to do is find its antiderivative, plug in its upper limit, minus, then plug in the lower limit into the antiderivative. And then this difference will give you the answer, which notice how this is much quicker. See, we know how to find antiderivatives of functions. So the shortcut is just find its antiderivative and then plug in upper limit minus lower limit. Okay, so before we do an example for FTC part 2, one comment I want to make. So commonly, so here's what we usually use. So this notation is often used when we're finding, when we're using FTC part 2. So here's what we're saying. If I say, hey, look, what's the integral from a to b of f of x dx, instead of finding the antiderivative and plugging in upper and lower limit all at once, we kind of want to organize our thoughts. So it's very common, I think almost every calculus book does this. What we do is we say, okay, first find the antiderivative. So I first found the antiderivative of this, and then we put this vertical line, lower limit, upper limit. So basically from here to here, all I really did is I found the antiderivative, and then this line is saying, look, the antiderivative has been found. Now I haven't yet plugged in my upper and lower limits. So once we do this, then we take the next step, which would be f of b minus f of a. So it's kind of like one step at a time. Let's first find the antiderivative. Here it is. And then once you do that, then you plug in upper limit minus lower limit. Now, one comment I want to make is this. In chapter 4, at the last section, every time we found the antiderivative, we had to put a plus c. I claim for the definite integral, we don't need to put the plus c, because look at what would happen. You don't have to put this in your notes, just kind of pay attention to what I'm saying. See, if I had said, okay, f of x plus c, what do you notice would have happened? What would I have? I would have had a plus c here, but then when I put minus plus c, what would happen? These c's would cancel each other out. So for a definite integral, whenever you find the antiderivative, you don't have to put the plus c. Okay, so the good news is the plus c doesn't need to be there. Okay, you could put it, but it's just going to be redundant, you know, because c cancels itself out. When you take capital F, plug in b, and then minus a, the minus would cancel the c's out. Okay, so for the definite integral, when you find the antiderivative, you don't need to worry about it as far as putting in the plus c. So let's look at our first example. We're going to say evaluate the integral from 1 to 3 of e to the x dx. See, now the good news here is I'm using the shortcut. They're saying evaluate this integral. If we're told to find using the definition of definite integral to find this, then we'd have to do it the long way. So for this, all we have to do is say, look, we're finding the antiderivative of this with respect to x. What is the antiderivative of e to the x? And we should all know it's e to the x. And then once I found the antiderivative, lower limit, upper limit, now I'm ready to plug in the upper limit. So it'll be upper limit minus lower limit. And then we could leave it at this. Okay? So there you have it. Notice how when I also found the antiderivative, I didn't bother with the plus c because, like I said, plus c is going to cancel out. Okay? Now, example 2, before we move on to FTC part 1, example 2 says, find the area under the curve of f of x equals to x cubed plus 2x plus 1 from 1 to 3. Okay, now this one, what is it that we know? The area under the curve of this function from 1 to 3, by definition, I mean, we learned that that's basically what a definite integral is. So in other words, what this is saying is find the integral from 1 to 3 of x cubed plus 2x plus 1 dx. Okay, so now let's do that. We find the antiderivative, which would be 1/4 x to the 4th plus x squared plus x from 1 to 3. So now I'm ready to plug in upper limit minus lower limit. So this would be 1/4 times 3 cubed, or 3 to the 4th, not cubed, plus 3 squared plus 3, all of this minus 1/4 times 1 to the 4th plus 1 squared plus 1. Okay, and then once you do that, now you simplify this. So this becomes, if you're to simplify this, it'll be 81/4 plus 12 minus 9/4, which all of this, so basically simplifying this breaks down to that, and then this simplifies to 30. Okay, so that's basically it. So this is the shortcut, which notice is a lot quicker than finding the definite integral by using the definition of a definite integral. So remember, the only time you should usually do things the long way is when you're asked to use the definition of a definite integral. Okay, now with that said, let's go to the fundamental theorem of calculus part 1. So FTC part 1 says the following. If f is continuous on the closed interval from a to b, then the function g defined by g of x equals the integral from a to x of f of t dt when x is between a and b is continuous on the closed interval from a to b and differentiable on the open interval from a to b. So basically we're saying, look, if f is continuous on the closed interval, then g, which is the antiderivative of f, is also continuous on the closed interval, and it's also differentiable. Well, obviously it's differentiable because what is the derivative of g? It's f, right? So, which basically means, and g prime of x equals to f of x. So notice what this is saying. See, this is where it gets a little weird. If I'd say, what's the derivative of g? You'd say, well, g is defined as what? By definition, g is the antiderivative of lowercase f. And the antiderivative of lowercase f, whatever it is, when you find its derivative, it brings you back to f. So here's where this FTC part 2 helps us out. See, if I were to say, look, g of x is what? Integral from a to x of f of t dt. So how would you, if using FTC part 2, how would this look? Since we don't know what lowercase f is, I don't know what the function is, and to be honest with you, I don't really care what this function is. See, what do I need to do here? To use FTC part 2, I need to find the antiderivative of lowercase f. So let's call it capital F. So what would that be? It'll be capital F of x minus capital F of a. So now, if I were to say, find the derivative of g of x, which is g prime, what is it? It's basically saying the derivative of this, or equivalent to the derivative of this. Now, what's the derivative of capital F? It's lowercase f. So this becomes what? Lowercase f of x minus, and by the way, f of a, see, x is a variable, a is a constant, and the derivative of a constant goes away. So notice how the derivative of g becomes lowercase f, except my variable from t changed to x. So basically, what is this saying? The derivative of the antiderivative is the original function we started off with, which is a little kind of, if you think about it, it's repetitive. We're saying, look, find antiderivative of this, Whatever that is, find its derivative, which brings us back to this. The only thing that happened in the process, my variable changed from t to x, which for obvious reasons, we could see from FTC part 2, how come my variable changed from t to x? It's because when I found this antiderivative, I plugged in x, then I said minus plug in a. And since a is a constant, when I found the derivative of this, it brought me back to lowercase f, but in terms of x, and constants go away. Okay, so that's kind of part 1. So you could see why I prefer part 2 before part 1, because hopefully this made a lot more sense to you. Because all we're doing here is we're finding what? The derivative of the antiderivative, which we're kind of undoing one another. We're ending up back in the same place. But that's what the fundamental theorem of calculus is all about. It's making a connection between derivatives and antiderivatives, right? So that's kind of what's going on here. So let's make a comment here. A couple of comments. We would say the derivative of g is, in fact, f of x, since g is defined as the integral, or in other words, another way of describing it is antiderivative of f. So g is the antiderivative of f, therefore derivative of g takes me back to f. Okay? So the second comment is, if f is continuous, then its integral must exist. Now think of it this way. Why must the integral exist? If f is continuous, imagine if I have a function f, and it's continuous from a to b. Well, if it's continuous, can't I close this off, and doesn't it have an area under the curve? So, and what is it? And the integral is the area under the curve. So obviously, if we can find the area, then the integral must exist. So we could see that, hey, look, if f is continuous, then the integral has to exist. Okay? Now, another way of expressing this, or the fundamental theorem of calculus part 1, is in Leibniz notation. If you remember, Leibniz notation is that whole idea with dy dx or d dx and so on. So before we do our next example, a couple of examples, I want to use Leibniz notation real quick, just to see, so you see how this looks, because the book will also use this. So using Leibniz notation for derivatives, we can write FTC part 1 as follows: as d dx, the integral from a to x of f of t dt. Okay, so what is this saying? This is saying find the antiderivative of f, and then this is saying whatever the antiderivative of f is, find its derivative. So it takes us back to f of x. Okay, so it's practically just saying, this says practically, if we integrate f and then find the derivative of f, then we get back to f. The only thing that changes is, like I said, the t changes to x, which we're making a transition. And of course, a, remember, is a constant. So when I find the derivative of a constant, it just zeroes out. Okay, so let's look at the next couple of examples, and then that'll do it. So this section was much shorter than last section, obviously, because we didn't have as much terminology, and the shortcut definitely is much shorter than what section 2 was. So we could say find the derivative of g of x equals to 0 to x of 3t squared plus 4t dt. So here's the thing. If we want, so what are we saying here? We want to find the derivative of this. So first of all, g is defined as what? The antiderivative of 3t squared plus 4t. Now, could you find the antiderivative of this? Absolutely, you could. But I claim we don't care to find the antiderivative of this because whatever the antiderivative is, I have to find its derivative. Okay, so it's kind of like this is the antiderivative and then find its derivative, which takes me back to this. So it would be a waste of your time. So what I would claim is this. I would say, look, by ftc1, what do we get? G prime of x is the derivative of the antiderivative of this guy, which brings me back to this, except this just changes my variable from t to x. So it should be 3x squared plus 4x. See, here's what I mean as far as you would be doing more work. If I said, look, evaluate g of x. G of x, by definition, is what? 0 to x of 3t squared plus 4t dt. Okay? You would say, okay, let me evaluate this. This is what? The shortcut means find its antiderivative. So what does this become? What is the antiderivative of 3t squared? It'll be t cubed plus 2t squared from 0 to x. Now, if you plug in x, you get x cubed plus 2x squared minus, if you plug in 0, it just zeroes it out. So what do we get? We get x cubed plus 2x squared. And then what we're saying, okay, well, this is what g is. Now, g prime of x is what? 3x squared plus 4x, which notice, what did I get? If g is x cubed plus 2x squared, g prime is 3x squared plus 4x, which is basically what we had here. Now, I just did more work than I really needed to because look, what were we saying here? When I said find the derivative of this guy, in other words, what are we saying? The derivative of this guy would just be the derivative of the antiderivative of this, which kind of takes me back to this. So the antiderivative of this, whatever it is, I'm finding its derivative, which is bringing me back to this. So you see here, I found the antiderivative by hand, and then I found its derivative, which took me back to the derivative of this guy is practically taking me back to the function that I found the antiderivative of. So it's kind of like I'm undoing it, okay? So it's just more work than needed. So anytime you're given an integral and you're asked to find its derivative, it's just saying, look, you're going to end up back with this because whatever the antiderivative of this is, who cares? We're finding its derivative, which brings us back, okay? So let's look at one more example. And then that'll basically do it. If I say find d dx of the integral from 1 to x to the 4th of cosine of t dt. Now see, here's what I don't like here, or here's what we should be careful about. It's this x to the 4th. So we don't like this, or we have to be careful about this. It's not that we don't like it. It's not as simple as going from 0 to x or a to x. It's going from something to a constant to something other than just x. So a common mistake people make is they say, oh, well, look, the derivative of the antiderivative would just be cosine of x to the 4th. And that is actually false. So this is not true, okay? We will need to use the chain rule here. And you'll see why in a minute, okay? So here's where, once again, the FTC part 2 comes in handy. So let's go one step at a time. Here's what we're going to say. This inside says find the antiderivative. The outside says once you find the antiderivative, find its derivative. And by the way, this should be x to the 4th, not just 4. So here's what we're going to say. I'm going to say, look, I don't care what the antiderivative of cosine is because whatever it is, I have to find its derivative anyway. So here's what we're going to do. We're going to say on the bottom, let's on this bottom say, let capital F be the antiderivative derivative of cosine of t. Although I could find the antiderivative of cosine, I could care less. You'll see why in a minute. So here's what we're going to do. By FTC part 2, what does this become? Just the inside part, right? The outside I don't care about. Just by FTC part 2, what happens to this inside? It'll be what? Capital F of x to the fourth minus capital F of 1. Okay, so that's all I did. I just said, look, the antiderivative of cosine, which we're calling capital F, plug in the upper limit minus plug in the lower limit. Now what do I need to do? I need to find the derivative of this guy, which what does that become? It'll be, so do you see how the chain rule is? Look at this. This is a composite function. I have capital F, and inside of it I have x to the fourth. So the derivative of this would be what? Capital F prime of x to the fourth times the derivative of the inside, which is 4x cubed. And then minus capital F of 1, this is going to be a constant, so the derivative of a constant is just 0. Now, remember, what do we say? Capital F is the antiderivative of cosine of t. This should be a t. So the derivative of capital F is just cosine. So what does this become? This becomes cosine, but instead of t now I get x to the fourth times 4x cubed, which now this is 4x cubed cosine of x to the fourth. Okay, so notice how when I found the derivative of the antiderivative, I came back and the x to the fourth, yes, was inside here, but because it was x to the fourth, I had to use the chain rule, because when you find a derivative of this, the derivative outside, which is capital F prime of x to the fourth times the derivative of the inside. So, and remember, the derivative of capital F becomes cosine. So this means just go back to your, we know that the derivative of capital F prime is cosine. Just replace your variable with x to the fourth. And so there you have it. Okay, so before we finish off this section, let me just formally give you the fundamental theorem of calculus, and then that'll basically do it. So the fundamental theorem of calculus. So this says, suppose f is continuous on the closed interval from a to b. Then we could say if g of x equals to the integral from a to x of f of t dt, then g prime of x equals to f of x. So we're saying the derivative of the antiderivative just takes you back to the function that you found the antiderivative of. The second condition is what? The integral from a to b of f of x dx equals to capital F of b minus capital F of a, where capital F is any antiderivative of f. That is, capital F prime will give you back to lowercase f. Okay? So that is basically it as far as this section goes. So we just learned the shortcut of finding definite integrals, and we kind of, this part 1 I guess is the weirder part. 2 is more straightforward, but if you have any questions, don't hesitate to ask me, okay? But that basically takes care of section 3.